Okay, everybody. So we are continuing with the second lecture of minimal submanifolds, and today we're gonna continue with variational approach. Remember last time we defined second fundamental form. So we denote by 2, and that's from Tn times Tn to Tn perp. Tn perp inside Tm. Remember we have a submanifold inside the we have a submanifold, or you can think of it as immersions if you want. So an n manifold inside m manifold, and we have the second fundamental form. So image, and we define to be defined as difference of roughly the difference of two covariant derivatives, two connections, two covariant derivatives. So you differentiate outside and you differentiate inside, and you take the difference. So that's how it were defined last time, remember. And another thing is that we define its trace because the image of second fundamental form is, so it's symmetric. So this is n times n plus 1 over 2-dimensional in general. So that it's too much, and but if you talk about H, which is the trace of the second fundamental form, then this gives you a one-dimensional information. You can compare this as like the Riemann curvature tensor and scalar curvature, or sectional curvature and scalar curvature. So sometimes you need too much information is cumbersome, and you choose to work with some function or vector field, so reduce it to a one-dimensional information. And so this defines a normal line bundle here, and this the image of second fundamental form is going to give you a bigger bundle in general codimension. Yeah. So those are some of the things we dealt last time, and today we're gonna deform this submanifold and find the minimality condition out of it. So we, from the surfaces, previously we were thinking that minimal surface equation is just being the mean curvature is 0, but we should see that it carries over how it generalizes to this setting in any codimension. In any codimension, we should see how it's gonna work out. Okay, so to be able to see that, right? So mean curvature. Vector field. So last time we said that this is going to be the correct way to generalize it. All right, so let's go over and the format, so you have n lies inside M manifold, and this is an M manifold I. So you can think everything works out with immersions as well, so that if you one parameter family of deformations, one parameter family of deformations of n is given by map phi. So map phi n times minus epsilon plus epsilon to the ambient manifold M, so that this deformation is going to be giving the submanifold N, or immersed submanifold N at the starting point 0, at time 0, you can think. All right. All right, so that's how you give a one parameter family of deformations of N. Let also some notation. Let for t in minus epsilon phi and t equals with, of course, n0 in this n0 is supposed to be n itself. And we're going to work on the coordinate system. So so x1 till xn be a coordinate system. So it's like we're going to choose it as a normal coordinate system. So pointwise coordinate system, coordinates around point P in N. Also suppose also here we make the assumption that also suppose it is a normal coordinate system around P. So we have the metric induced from M, and you obtain metric from induced from M, so that you can talk about normal coordinates. So you take a normal coordinate system for just N only, and then then you can think about extending this coordinates to the epsilon part with the new parameter t is a coordinate system of n times minus epsilon plus epsilon around the point p0, of course, p0. Okay, all right. Then we have special vector fields, standard vector fields along this deformation. Vector fields along this deformation are going to be vector fields of the standard vector fields of the deformation. So first one is going to be the ones through coordinates xi. So which is can be obtained by d phi of partial xi, or if you want to choose star notation, you can write it as phi star partial xi for I from running from 1 to n, and t. Actually, t is of course more standard, so ei depends on the coordinate you choose, but t is coordinate free. Well, that depends on the parameter t, but its direction is coordinate free at least. So d phi, again this time just push partial t to the manifold, or just write in terms of partial t notation if you want. All right, so normal coordinates gives you restrictions on these. So normal coordinates imposes, let's see what they impose so that we're going to use it later. Remember, the metric becomes diagonal at that point, and also all derivatives become diagonal, so that Gij at P0 is going to be delta Ij. So the restricted metric Gij P is delta Ij, so that at 0 that's also true, and the covariant derivatives are going to be all 0 around at that point as well. Okay, so those are the implications of normal coordinates. So those are going to help us for great help for the computations, and we're going to differentiate the area so that to find its minimum or maximum or critical points, so that we have to talk about an area element to define areas and or volumes depending on your dimension. So DAT is going to be equal the area or, or volume depending on the dimension you're working. So if it's a surface, then it's going to be area element, of course, area element of NT. So if you think it as a surface, so that's the area element of the minimal surface, the surface, subsurface. So with respect to the induced metric. And we make the abbreviation of GXT to be the determinant of the metric, determinant of the metric J PT, and in that case you can write the area element as remember the square root of the determinant times the coordinates volume form. And right, and remember, so we're gonna make a special care about the A0, so that let's just write it once again for that one, so that that's the original submanifolds area element, and then the others are pushed forward. And if T is sufficiently close to 0, if T is sufficiently close to 0, T is sufficiently close to 0, then we can write one of them in terms of the other one by, so dAT is going to be equal to, so you can just think that you're dividing these guys, and this is going to be equal to some multiple of dA0, and that multiple is the quotient of 2G's, or J xt equals. So let's see whether I can fit it here. Square root of GXT divided by square root of GX0. Okay, so for if you are sufficiently close to the submanifold, then you can look at this ratio. So to find the variation, we should differentiate the volume form or area form, and expand that. To be able to do that, we should be using the derivative of J. At this point, let me sketch a small picture here. Make a small picture here. Here, for example, if this is N0, then so we are all inside big M, and you have a one parameter family of deformation. Actually, this deformed surfaces or submanifolds can cross each other as well, but if it doesn't have to be like this. yeah, they can cross themselves, like after a while, for example, something like this can happen. These are NTs, maybe N minus T's are in that direction, and you have variational vector fields. Vector field variational vector field partial T here. Or here, partial T, and so what else we defined? We have partial xi's. Over n0 in those directions. Yeah. Okay. All right. So that's how the picture looks like. Let's again remind you what we are doing. So the first variation for the area or volume of the submanifold N. So that's what we are heading to. So to do that, we should compute the derivative of J. Compute the derivative of J, J prime PT, and that's derivative with respect to T, of course. With respect to T, so J prime P0. So let's start. We only gonna need it at first on the original manifold, right? So if you do that, so then let's partial J partial T P0, and so remember what J is. What J is. By the way, I didn't. It seems that I didn't share the slides. Let's. Let's take a moment to do that also. And so, right, let me start, let me share it, and then we continue. So that you can go back and forth with the slides. So I just noticed that when I'm returning to the previous slide, you can do it on your own. Okay. All right. So if T is sufficiently close to 0, you can write it like this. And remember, so when we're differentiating, we're gonna making use of that one. So it is just differentiation of the square root, right? So it is just, if you abbreviate, this is 2 radical G 1 over 2 radical G times the derivative partial G partial T, and the rest of the term counts like a constant G P0. All right, GP0, and you should evaluate this at the point P0, of course, P0, of course, and so you can easily simplify. So the first time, so you see there are similar terms, and if you just join them together, 1 over 2 radical GP0. Oh, we don't have any square root for that one, right? So 1 over 2 GP0 times G prime P0, and here remember we have at the point 0 we have normal coordinates, right? So this happens to be equal to 1, so that you're gonna get 1 over 2 G prime P0. Okay, so that's what you get from the derivative of J. J this one is happening from normal coordinates. And anyway, we have to differentiate G. We have to differentiate G. To do that, now differentiate now differentiate G, which is the determinant So in this kind of computations, at some point you always need to differentiate the determinant. So that's one thing, and there are multiple ways to do that. So here I'm going to show another. Some of them are equivalent to each other, of course, but this. Let's see how we deal with that here. So you write G as, by definition, G is the determinant Gij, and you can write this as just taking the determinant of the matrix. Remember, you can open through the first row G1J and multiply with the determinant of with plus minus sign of the rest. Cofactor matrix. Where Cij, it's okay. Okay. Hope nothing's disappeared here. Where's Cij? Cij is R. Cofactor, a matrix coefficients of Gij. in this case, let's see, we can have enough room for that. Maybe I should, maybe that's, we're going to fit into here. Okay, therefore, G prime P0 equals determinant Gij Pt differentiated, and P0 is feeded, and that's going to be equal to, okay, so we have the definition upstairs. So just so it's a summation, it's a sum of products. So let's use the Leibniz rule and then proceed. So we have a summation running from 1 to n times, so you differentiate the first one, G prime 1j P0 C 1j P0 plus G1j P0 stays, and C prime 1j P0. Okay, so that's how we start, and immediately you can realize that so we have some simplifications here, like for example, because of again the normal coordinates, the C1j term is going to be Kronecker delta, and Gij is automatically Kronecker delta. So to see that, so if you write down the metrics, let's see, I can fit in here. So Gij, maybe I can fit here. Gij, the point P0 is going to be equal to, it is diagonal at that point, remember, so 1, but if you open through the first row and column, so you have 0 here, and remember you have a the rest of the column supposed to be 0, right? So here and so this row, this column included in Cij if j is not equal to 1. That makes it determinant of Cij equals 0 for j is not equal to 1, and C1j is of course 1, right? That determinant. All right. That was how you can of course see it. Okay, so if you do that simplification and continue. Okay, let's see whether we can fit this formula here. Okay, and if you continue on the summation, so G ij prime P0 delta delta 1j plus delta again 1j. Let's not make any typo here. Delta 1j C prime 1j P0 and so after we are summing over j, remember, and this is also one, right? So summing over j, and after application of Kronecker deltas, you only left with G prime 1 P0 plus C prime 1 P0. All right, so that's what you get out of the differentiation of the determinant. But as you can see, this leaves you C prime with C prime 1 so this is nothing but erasing the first row and column, determinant of the reduced matrix here, so that you can you can do that again, then so G prime 1 P0 plus, if you do that for C11 prime, so the smaller matrix with repeats itself, then you obtain a similar result. So G22 prime, just arrange the indices accordingly, plus C22 prime P0. All right, so if you continue like this, at the end, at each time you're gonna get the next G term, G prime and P0. All right. So that's at the end you obtain a result entirely in terms of G's, so that your derivative of the determinant becomes G prime P0. It's going to be equal to the sum G prime I at the point P0. I is running from 1 to n. All right, so that's how you got the derivative of the determinant. Derivative of the determinant, and so if you write the ingredients in terms of our new notations adapted to the deformation, that was by GII prime was by definition differentiating in t direction. Of EI inner product with itself, and our notation was T for that one, remember. That's the notation we fixed. And that's, if you do it, it's going to be, if you do the Riemann connection axioms, symmetric and torsion-free axioms, so that's going to be nabla T, E, EI, and this is going to be equal to, so, and you use the symmetry, that was torsion-free, and you use the symmetricity to exchange the place of the derivatives inside the covariant derivative. So nabla EIT plus TE1 TEI bracket EI all right, so here this is nothing but, this is going to give you 0 because it is nothing but partial t, partial x minus partial x, partial t, the Lie bracket, so that we, because that forms a coordinate system. All right, so I double I prime becomes twice nabla EI T EI partial t partial x equals 0 because x1 x and t form a coordinate system for n times epsilon. All right. All right. So it is okay. Global defined. All right. Then we are ready to make our main. We're ready to make our main variation. So write the projections of T. Write the projection of T, the variational vector field. You can call it maybe variational vector field. To make it a difference from others. You can look at its tangential part and its normal part. So okay, so this is the first one belongs to the tangent bundle, and second one belongs to the normal bundle inside M. And then so we're going to be differentiating. We're going to be remember we are going to be differentiating this quantity here, so that we should be. Let me emphasize that. So we should be differentiating this quantity here, because that's what lies inside the volume element, right? So let's try to take the derivative of this one, and then we're gonna finish our task for today. So we should simplify that quantity to be able to understand our first variation, result of our first variation. So we have a sum of sum of GII primes, so that corresponds to that sum here. Remember that's how we find it. So the derivative of the determinant is that some GIA prime, and GIA prime is that this covariant derivative term, the sum of that covariant derivative term, so that just we all need to simplify that term as our ultimate goal for today. So nabla EI T EI. If you want to simplify this using, so first you project, and then we're going to use connection identities. First you project into tangential and normal coordinates, normal directions. So T tangential part EI plus the sum EI, the normal part, and so here, if you look at carefully into the first term, so after taking covariant derivative with respect to EI, and because EI is also happening inside Tn. Remember, these are EIs are inside Tn, so everything happening here lies inside. You can think it entirely happening as inside N, so that that's nothing but divergence of the vector field TT plus for the second term you can use the connection identities, so EI Tn EI minus the rest of the term Tn nabla EI. That's just opening the Leibniz rule from the other side, and remember here this is a normal and this is a tangential vector, so that their inner product is 0, 0, and next what survived is going to be only the second term, the last term here, only the last term here. So if you divergence TT plus the sum Tn minus nabla EI, and here remember this is nothing but This is nothing but our definition for the second fundamental form. Second fundamental form. So what left over at the end is going to be if you push the summation inside. So that's this summation on the second fundamental form, and we know what does that mean. Remember, that's just taking the trace, divergent TT plus Tn times H, so that this is trace of the second fundamental form, which is the mean curvature vector field, remember. All right, so as you can see from the differentiation of the volume form, that's how the mean curvature vector field comes up naturally. So if you collect what we did into one line, is just summarize what we did. Okay, maybe summarizing. Summarizing what we did, the first variation for the volume form, for the area or volume form area, form at the point P0 is going to be d over dt at t equals 0 of at dat volume element. That's, you can think it as infinitesimal volume, so you want that change in that should be equal to 0, remember, and that was remember, it involved J inside DAT. Let's write the correct coefficients. DAT. Okay, let me just write it once again, because we wrote them separately, so that let's give a chance to look at all things together. DA0, remember, so that you have to differentiate. We had to differentiate J, and what we find is, remember, 1 over 2 G prime P0 DA0. So these are repetition of what we did, the summary of what we did, and then G prime P0 was nothing but the sum of GII primes DA0, and it was computed to be equal to twice the sum of nablas, and 2's are going to cancel, of course. Nabla EI T EI DA0. All right, so, and in the final stage, we find out that that's nothing but yeah, so pretty long. After a couple of steps, we able to arrive the divergence plus the mean curvature vector field. All right, so that's how we reached, and this is also happening, of course, at P0, at the point P0. All right, so here, if your variation vector field is compactly supported, then divergence is gonna drop out. So let's consider that case. That case, if T is compactly supported, T is compactly supported on N. If the variation vector field is compactly supported N, for example, if N is compact, then it's of course compactly supported, or if N is open and at the boundary you expect the variation vector field to end up with 0, then it becomes compact supported again, so that in both cases you can use the divergence theorem. By the divergence theorem, d over dt at t equals 0 of dat area of t, area of n and t, so this time, of course, it's not pointwise 0, but it's integral is 0, so that you should be looking at the area of nt to be able to use the divergence theorem, and that's going to be equal to the integral of this quantity. Yeah, h the a0, the integral over n, and then it's going to disappear, of course. And of course, remember, so you no longer, so and h is belonging to already to the normal bundle, right? So maybe nn, let's just write nn at this time, normal bundle, so that you don't need to take the normal component of the variation vector field. So the whole thing is gonna also work out pretty fine to make it look better. So t h the a0. Okay, so all right, so at the and in this setting, as we can see, we only have as the new term, we only have the mean curvature vector field, so that you can this helps you to come up with the definition to be, so our general definition, so our generalized definition reads as follows. So as an outcome of the computation today, we can now define what is a minimal submanifold in the general case. So, and you can define it in the immersed submanifold context to make it in full generality. So an immersed submanifold and M to M N to M is called minimal if its mean curvature vector field vanishes identically. That is what we called H supposed to be equal to 0. Okay, let's put an arrow as Peter Lee did, so that once we don't need that, but just remind once that we are not using the function here. And I'm going to finish today with an exercise so that everything here can be applied to, of course, curves. Also remember this minimal submanifold definition is the critical point. That's it's not defined to be the minimum or maximum. Remember, so remark. Defined it as a critical point. Not as a maximum, or not as a minimal or maximal point. Only. So we're going to come to that. That's related to the stability of minimal submanifolds, and finish with an exercise, an example geodesic equation. So curve take a curve, take n to be a curve parameterized by arc length with unit tangent vector E, and you can, if you write the first variation formula, for just the length, in this case d over dt, t equals 0, lt is going to be equal to tte from L to 0 integrate taking the difference from L to 0 and integration from 0 to L Tn nabla EE. Yeah, so so from here, just compare this with the minimal, compare this with the geodesic formula and find the geodesic equation from here. Okay, so that's gonna be a nice homework exercise. All right, yeah, next time we're going to talk about the second variation formula and stability. I just told you that we didn't define this as a minimal or maximal. So how to decide minimum or maximum. So next, in the next lectures, how to decide that a critical submanifold is minimal or maximal. I'll decide that the critical modes have maybe, yeah, has minimal or maximal area. Is it minimizing or not? So for that we need second variation formula, second variation, and the concept of stability. Those are going to be the topics for the next lectures. Okay, yeah, that's all for today. So any questions? How we are sure that there is minimal but not maximal? Right, so I just explained that once you find the critical points, it's not yet clear, and we should do the second variation and stability, and it's going to be coming next. All right, but we make minimal surface definition as critical points and then select among them some and see. We're going to see whether a minimal surface is minimizing or maximizing, or how it behaves by looking at its second variation. Okay, another question? All right, thank you very much.